We continue to work through section 3.3. We've already established how the first and second derivative tell us about more of the shape, the increasing, decreasing, and the curvature, the concave up, concave down. But now we come back to the relative, the local max and mins. We initially introduced these in 3.1, and we tried to distinguish them from the absolute max and mins. Initially, their definitions looked very similar, but we already established the difference. The absolute max and min is all about a list of candidates, which included the endpoints and the critical values, and then we had to find the y's for each. Biggest y went with max, smallest y went with min. But for relative max and mins, it was all just about being a peak or a valley. So, if we look at relative max and mins, let's go back to that same original graph f. Again, just looking at the function, there's a valley, so x equals -3 would correspond with a relative min. X equals 1, that's a peak, so that would be a max. And x equals 3 would be another minimum. It doesn't matter that this minimum is above the other as far as local relative minimums, any valley counts. And these are questions, sometimes the book will say at what point, so you will need an XY pair, but most of the time, especially when I give problems, I like to just ask where. So once again, all you need is the X. Where does this function have local max? Where does it have local mins, if any? A function doesn't have to have them. Well, this function would have mins at x equals -3 and x equals +3, and a max at x equals 1. We've also established back then that what's special about these, that they occur at critical values. How do you get a peak? How do you get a valley? You either end up with like one of these round hill bottoms or hilltops, which has a horizontal tangent line where the derivative is 0, or you get one of these sharp peaks or sharp valleys, which would be a spot where the derivative is undefined. But now we could finally bring it all together. So how do we find local max, local mins? If we have the graph, like we have here, we could just literally look and get them like we've been doing. But now let's add a little bit more. To find these, finding our relative max and mins, we'll start by finding our critical values to give us our sense of candidates, but then we will think about the increasing, decreasing aspect. This is where the book makes this whole big table, but if we understand this well, then this next part will make perfect sense. How do I know this is a minimum? It's a minimum because we were going down in front and going up after. That's what made that a minimum. So that my derivative sign changed from negative to positive. How do I know this was a maximum, a local max? Well, I went from going up, increasing, followed by going down. I went from derivative being positive to the derivative being negative. So that's what we're going to use here. We're going to realize in just another minute that answering questions when we are given the equation, answering where a function has local max and mins is going to be so similar and related to knowing about where that function is increasing or decreasing. That's going to be almost the same exact work will give us the same answer. So we'll find our critical values. We will establish our derivative test interval, our first derivative test interval, and we'll interpret these individual x's. So let's jump right into some problems. Let's establish where do the following functions have local max or local min, if any exist. Just like when we did the absolute max min problems, that possibility that we may not have one, that's certainly something we have to consider. And instead of just saying finding local max or local mins, I might also establish something like, just say find the local extremes. That would satisfy all. Some of the problems in the book have you first find the critical values and then declare if each one is a local max, min, or neither. So there's a few subtle variations on the question, but we'll focus on this one. You'll see those minor variations don't really change much at all. So here's a question. Let's start with problem number 1. And let's use a of x is x squared minus 4x plus 3. I'm going to do these questions with the exact same functions that we did when we were asked about increasing, decreasing. So how would I know about the local max min of this function? Well, from what we're establishing, what we're saying, we'd have to do all this exact same work. So I'm just going to cut to the chase, everybody. I'm going to copy this test interval. I've got a prime. That was it. I mean, I could copy more of the test values, but this is really what I need. I took the derivative, I set it equal to 0 or where it was undefined to find the critical values. I established the first derivative test interval, and now I will interpret my solution. What happens at 2? Well, I'm going down before I get to 2, and then I'm going up after I get to 2. So what happens right at 2? That must be a minimum. And that's it. X equals 2 would be a local minimum. What about local maxes? There are none. There was only one critical value. It was a local min. We did not get any local max. And go back to what we said when we were doing the increasing, decreasing. That really is the graph, everybody. This function is just a straightforward parabola. And with that idea of local max, local min, it has a valley. There is no peak. So that's it for problem number 1. Let's get to number 2. Number 2 was b of x, x to the 5th, plus 5 halves, x to the 4th, minus 5x cubed, plus 1. And same thing, everybody. I'd have to get to the test interval. So I'm not trying to cheat here. I just try and establish it's the same work. Being asked, where's this function increasing or decreasing? Being asked about the local extremes, you're really doing the same work. Get the critical value, step 1, get them on your test interval, set up the test interval, and then reuse the plus or minuses to do increasing, decreasing. Now we focus on the x's and what happens before and after to figure out max or min. So for b prime, we had -3, 0, and 1, and we went plus, minus, minus, plus. That was our interval. So what does that tell me? Well, I'm going up, then I get to -3, and then I start going down. Going up, get to -3, turn and start going down. -3 is a max. At 0, well, I'm going down, get to 0, but then I keep going down. 0 is neither a max nor a min. I don't get a peak or a valley. But then at 1, the negative before means I'm decreasing, going down. The plus after means I'm increasing, going up. And now I'd get a minimum. I'd get a valley point. I'm not drawing the whole function. I'm just concentrating on the plus or minuses here to just establish ups and downs and using these values as the in-between. Going up until here, then going down after. So these little pictures fill me in that x equals -3 is a local max and x equals 1 is a local minimum. That answers the question in this form. One of the alternatives I said, if I said find all the critical values, classify each as a max, min, or neither, well, now you just include this information as well. You'd point out these two in the exact same way, but then you just note x equals 0 is neither. Technically neither a max nor min, but by just saying neither is enough for me. Okay, we're still not stopping here. We're going to go right into number 3. C of x was the x plus 16 over x minus 3 function. Once again, everybody, Perfectly fine for you to take a few minutes, redo the work to get to this, but that's what I keep establishing. Such completely different sounding problems that require such similar work. So in number 3, we already had our test interval. So let me just recopy that. We had C prime, we had -4, 0, and 4, and we went plus, minus, minus, plus. Very similar, everybody. Going up, going down. You don't have to draw these. The more you get used to this, the better you are. If you follow the book exactly, they write up this whole formal theorem and talk about, well, if you go plus minus, then you get a max. If you go minus plus, then you get a min. I hate that extra memorization. Again, if we understand that first theorem about how the signs, the plus or minuses, tell us about the ups and the downs, that is exactly what that box is telling us. Plus, minus, don't just memorize that's a max, understand why that is a max. You're going up followed by going down. Whether you actually draw it or you just kind of like think about it the way I'm doing here, either way that establishes that is a max. Going down, still going down. This actually wouldn't be connected. That would actually be an asymptote here. It would actually look more like this. But it doesn't matter. It's still nothing. There is no peak or valley. That still ends up being a neither. And then the minus plus going down followed by going up would make 4 a minimum. I really don't mind if you leave your answer like this, but it's not a bad habit to come back, back in the question, back in the beginning, and get that in a nice spot that we could see. So x equals -4 would be our local max. And x equals +4 would be a local minimum. And just like I said on the previous one, if you were told to find all critical values, well, technically this would not be a critical value. Not too surprising, it's a neither. Again, it's not a bad habit to establish. Always think of all your important x values. Okay, so one more here. Let's finish this idea. Number 4, let's look at d of x was the 5 minus x quantity cubed and the 2x plus 8 quantity squared, and we ended up with this test interval. We had d prime, we had -4, -2/5, and +5, and we went minus, plus, minus, minus. Same thing. Minus, plus, going down, followed by going up, that's minimum. Now, before -2/5, we're going up. After -2/5, we're going down, up to down. That is a max. And then the minus, well, I'm going down, and I'm still going down. 5 would be an either. Just before I write out this answer here, I just want to point out one quick thing here. Coincidences, everybody. These 3 had 3 important x values, and they each had 1 max, 1 min, 1 neither. You never know, everybody. That's just what happened to these problems. You do more in the book, maybe you get 2 maxes, 1 min. Maybe you get 2 mins and 1 max. Anything can happen here. That's just a coincidence that what happened in these few problems. So let me just sum it up again. So x equals -4. There's my local minimum. And x equals, I'm sorry, not 5, -2/5 as my local max. Okay. Well, okay. So relative, local mins and max, nothing too bad. Really connects with the first derivative. Do we have something that connects with the second derivative? It's a common question. Maybe you're not exactly thinking of that, but that's where we're going next. I will come back. There's one more thing to say about the second derivative to local mins and max, but we'll get to that in a few minutes. Let's establish the second derivative idea. We have another important term that we have to define. We have what we call points of inflection, or inflection points. Same thing. These will be what connects that idea of second derivative and concavity and the original function. What is an inflection point? A function f of x has an inflection point, or a point of inflection, where the function changes concavity. The points of inflection are going to be very similar to the local mins and maxes. We had local mins and max when the first derivative shifted signs, because if you went up then down, you had a max. If you went down then up, you had a minimum. But there we had two different things to establish. Here, if we have an inflection point, whether you go from concave up to concave down, or concave down to concave up, either way, that is an inflection point, a point of inflection. I again often just ask where, but if the book says find the points of inflection, they are a point. Once you have the x, go back to the original function to get the y. So that's all we're looking for here. And now I'm going to take those second derivative examples. We are going to say, we're going to ask the question, where do the following functions have points of inflection? If any exist. It's possible the function has none, just like it's possible a function does not have a local min or a local max. So let's start this off with number one. Let's use the e of x was the 1/4 x to the 4th plus 2x cubed minus 2x plus 7. Again, we did this back on page 4 with concave up, concave down. We made our second derivative test interval, and we ended up with this. We had -4 and 0 as the important x's, and we went plus, minus, plus. So in that problem, we established these were concave up, and this was concave down. But now all we're going to do is now we'll focus on the individual x's. I hope you realize there's a lot of similarities. Finding points of inflection is very similar to finding the local max and mins. Just using the second derivative test interval and focusing on the x values, using the signs to interpret what's happening at these x's. Finding the concave up is similar, or concave up, concave down, is similar to the increasing, decreasing. Just again, first derivative for the increasing, decreasing, use the signs to get the appropriate intervals, and then concave up, concave down, second derivative, and the pluses and minuses go with your respective intervals. So again, a lot of similarity. This is why this is a very tough and long section. Those two theorems at the beginning kind of established everything, but that really opens up a lot of doors to a lot of problems. There's a lot of similar work, and it's easy to get confused. When should I use the first derivative? When should I use the second? So a lot of good things to practice here. But now let's just wrap this up. So the points of inflection, well, concave up to concave down, you change concavity. So -4 is a point of inflection, and so is 0. With local max and mins is a difference going plus minus to minus plus. But when we're talking about points of inflection, there is no difference. Both x minus 4 and x equals 0 are both points of inflection. Number 2, we'll do similar with g. We had g of x was 4 over 3x minus 3. We ended up with this test interval. We had 1, we went negative plus. But here's that one little tricky point, everybody. And it was the same thing we said with local max and mins. Yes, we changed concavity, but 1 is not an inflection point because 1 is not in the domain of the original function. That's the only catch. It's so tempting to just say x equals 1 is a point of inflection. We got the minus plus the same way we had here. The sign changed, but that's the one extra catch. A point of inflection is where f changes concavity, but it has to be at a point in the domain. The function actually has to exist there. So this, it's a little trick. It's a little tricky, I should say. This has no points of inflection. Again, we do get the concavity change, but the issue is there is no actual point. Come back to what I said a moment ago. I only asked where, but if I said find the points of inflection, let's do this one quickly. You know x is 0, you plug 0 in the original, you get 7. So 0, 7 would be the point of inflection. You could do it here. It's just a little bit trickier with the arithmetic. Here, you take x equals 1, you try to plug that in to get the y, you get 4 over 0, which is garbage. That's undefined. So that's the reason we're getting no point of inflection here. It looks like 1 should be a point of inflection, but it actually has to be a value that the function is defined for.